Oh no, we did shifts on 7.3. So 7.4, we took a look at another set of what they call operational properties, and that's the relationship between in the real world multiplying something by some power function, power polynomial, and then in the Laplace world it becomes a derivative of something. We talked about the convolution, and the convolution involves an integral. And if you looked at the notes, so in our class last time we did instead of doing the convolution, we did something else. But then I said it was probably a little bit easier to do the convolution. So um, if you didn't take a look at the notes, it kind of looks the convolution looks like this, and it's just a lot of stuff here because it requires some trig properties, and so I walked through all the trig properties and all the trig integrals that are needed, and then eventually came up with the same result that we got by doing it the other way. And of course, if you have an integral like this, you could just plug it into Wolfram alpha or something, and then it'll immediately spit out the correct answer without having to go through and try to remember all your trig identities and stuff like that. So that result here is summarized in your notes if you look at them. So the convolution is a way to get our solution if we have some information about your results in the Laplace world, and you want to bring it looks like it's a product of two Laplace transforms. You can bring it back by identifying those functions and then putting it through this integral. And so there's one more that we didn't get to cover, and that's the transform of an actual integral. So here's a little bit of the new stuff. um, in case your differential equation um, has an integral in it, in which case it wouldn't be necessarily called a differential equation. It would be called the integral equation. They call it an integral differential equation, and and that's just going to be the Laplace transform of that is f capital F of s divided by s. And then more importantly, if you have in the Laplace world, if you have some function that you know the Laplace transform of, and then it's divided by s, you can bring it back to the real world through this integral. Michael. Yeah, well, if you do that, then yeah. So not that I don't know if it's necessarily elementary or not elementary, but I think instead of having derivatives in your equations, you have these integrals in your equations, and then um, and I don't know how necessarily how easy it's going to be because you're going to have the integral of f, and then you also have f involved. And so when you take the derivative, then it becomes just another differential equation. And then yeah, so you could do it that way, I suppose. So you have one or two homework assignments, but I think those particular assignments, are pretty straightforward when it deals with this integral. So I'll let you deal with that. I do want to go to the next section, and the next section introduces us to our latest, newest function, 7.5. So the Dirac delta function, sometimes known as just the delta function, is a special type of function that now for sure we can't um, solve for these differential equations using some of the other techniques that we've known, because this is a special type of function that really is built for, Laplace function is built to be able to handle this. So let's start by defining the delta function. The delta function is called a unit impulse function with the following properties. And the property is that it's zero everywhere except for at exactly one point, and at that one point, it's infinity. And the way they define this, you can mathematically define this, as weird as it might seem. And the way they do it, I think they do it in the textbook, is that if you have a t sub 0 here or something like that, then what they essentially want is an area of 1. So let's say this thing is 1 unit to the left and to the right. And so the height has to be, I guess, 1/2. So that the area of this function is 1. And then what they do is they take these points over here and they let those points, distance from t naught to one of those ends, eventually go to 0. And so you have a series of finite functions that at the limit eventually goes off to infinity. So it really just becomes that one point where everything is 0 except for this one point where it goes off to infinity. So that the area under that curve is equal to 1. Yeah. You're you're not splitting it up, you're stretching it up. And as you stretch it to keep the area equal to 1, your height, your base has to go to 0. So your height goes off to infinity and your base goes to 0. And then at any time in the middle you stop, your area is always going to be 1. And then at infinity, it just goes off to infinity, and then supposedly your area is still equal to 1. One can think of this physically as, if you imagine your oscillating spring problem, if at some point, either at the very beginning or at some point after you've started to let the spring go, you hit it with a hammer. So that hit at that exact point or that exact time is going to be that impulse function where it contributes like an infinite pulse, and then you let it go again and see what happens to the rest of the spring. So it's so the idea is that this is just going to be I don't know. So that's how the impulse function is defined. Hammer at a spring, yeah. You're hammering the spring. So you're giving it a big jolt. You're Yeah, so the red is that big jolt. It's just that exactly at that one point in time. The 0 to infinity just says that it's happening on the positive side. So some point t naught, so t naught is going to be some number that's bigger than 0. at some point T naught is when you're going to hit that mass in the spring. Well, delta of T is just the impulse that happens at 0. So delta of T minus 1 is that you let the spring go, and in 1 second, then you hit it, and then that's when your pulse that's where your pulse happens. No, no, the rectangles, the blue rectangles are just to show you how they came up with this definition. So the blue rectangles are just a definition. So the red is what's happening. So this graph over here, if I were to graph this in red, the graph of the delta of T would just be the impulse function. And when I draw this red line, it technically goes on forever. And then that's the impulse function that happens for delta of T. Now delta of T minus 1 is an impulse function that happens at 1. And so at 1 is when we'll see that spike. And then nothing happens. You just do the spike, and then that's it. So it's you're oscillating, and then you hit it, and then you let it go again. No, the blue rectangles are not part of the picture anymore. The blue rectangles are part of the way to derive your delta function. So in terms of an actual application, you have an application, a regular spring, and whatever those spring problems that you guys have been doing. And then at some point you hit it, and then you let it go, and then that's it. And so we can take a look at the graph. We'll do an example and see if we can look at the graph of it. Yeah. I know. So you hit it. You're supposed to hit it hard enough to represent infinity. And so it's just a definition of the delta function to make it, because there's no space to the left and to the right of the x value, right, or the t value. Because there's no space to the left or to the right, and you have to have area equal to 1, this thing has to go off to infinity. You know, realistically, you don't evaluate things at infinity, but it's going to be a large enough scale. Yeah. That's a good function. That's a good question. I don't know. So in any case, the whole point is that we want to just be able to use this as an action, and then be able to solve our differential equation where the delta function is part of the differential equation. And we're going to do that by doing a Laplace transform. I think we could take a look at that if we take a look at an example. So in any case, the delta function has a transform that sends your delta function into the Laplace world as an e to the negative st sub 0, whatever t sub 0 is. And at the origin, or at t is equal to 0, then the delta function is simply equal to 1. All right, let's do an example. There's a bunch of examples here. Should we do number 1 first? try to ease into this. So we have this differential equation, and this differential equation uh, is equal to the delta function t minus 2. Now, like I said, there's no, I mean, you can try to solve for this using, what's that called? Um, piecewise, or I was thinking the mu, what's that called? Integrating factor. So you can try to solve for this using an integrating factor, but then you'd have to take the integral of the delta function, which you might be able to do. But the idea is that if you see a delta function in your equation and you're trying to solve for this differential equation, then you definitely want to use Laplace transform. Yeah. Well, if you're looking at the spring problem, which would be like a second order differential equation, then it would just, you let it go and then the spring just oscillates until you hit it. Yeah. Yes, it's the external force. All right, let's solve for this. Let's take this to the Laplace world, and we take it to the Laplace world. It goes into the first derivative is s, capital Y of s, um, minus y of 0. So that's your first derivative, minus 3, and then you have y, and then the delta function. So this is where we get to use the delta function now. And that's equal to e to the negative 2, e to the negative 2t. Nope, negative 2s. Yeah, because we're in the Laplace world now. So now we're in the Laplace world, we're solving for y, capital Y. So s minus 3 factored out a y, and then y of 0 is equal to 0. That's equal to e to the negative 2s. And so y is equal to e to the negative 2s divided by s minus 3, or write it like this. Now, what we need is we need to wait to get back, and so we need the Laplace, the inverse Laplace transform of this. So is there anything in the Laplace world where we have an exponential function and then we need to bring it back? You guys remember anything that has that capability? Yeah. There's a shift in one of the translation theorems. There's a translation theorem that happens in a t, and there's a translation theorem that happens in the s. Okay. So this is going to be some sort of a translation theorem. So let's say we're ready to move our action here to bring this back into the Laplace world by doing the Laplace inverse. And then what is that translation theorem that we need? It's Laplace of something, t to the something. Is it t or is it? You guys remember? So we're inverse Laplace of e to the negative as, capital F. Okay, so that's the formula that we want, right? And so our f of s is 1 over s minus 3, and then we have e to the minus 2s. So this translates into this is e to the 3t, or negative 3t. So this is e to the 3t. And then there's a unit step function that we took that shifted this. So e, it happens at 2. Oh, ft minus a. So all right. So then our final solution, your y of t is equal to, it's just that, right? There's no other extra terms. So e to the 3t minus t minus 2 u of t minus 2. Okay. U represents the unit step function. Zero and 1. I think we only look at, we've been only looking at the positive side of things. Because capital F of S is 1 over this, and the translation back from F, capital F to little f is the exponential function. So for that, we needed to know our other Laplace formulas. So we need to have these things, really have them handy. What is it? AT. Okay. Any questions? All right, let's try another one. See, number 6 has 2 of them. All right, let's try number 6. So for something like this, we can imagine that this is some word problem. About a spring. So there's no prime. So that means there's no damping factor. And then we can just say whatever we need to say to imagine that this is a spring or whatever that does certain things. So this particular problem has a couple of places where it looks like this thing gets hit. So I would imagine, and this is just a guess, and what we could do is we can check our answer and by graphing it. But it looks like um, this has an initial position, y of 0 is equal to 1, and then y of 0 is equal to 0. So this would be a case where you would pull the spring down, and then you would let go, and so it would start to oscillate. And now at t is equal to 2 pi seconds, you would hit it, and then it would do something. And then at t is equal to 4 pi seconds, you would hit it again, and it would do something else. So I would imagine a regular oscillating, and then you hit it. I don't know where that would get hit, assuming. So right here, it hits, and then maybe it jumps up, and then oscillates again, and then it hits, and then it jumps up. So it doesn't. I know the graph sucks, but it's yeah. There's some drastic change to the graph. It'll jump up or whatever, and then uh, it could, but in this case, there's no damping. Yeah, so it'll oscillate back. Maybe not to its original thing, but the the what's that omega called? The frequency won't change, so it'll probably keep the same frequency. The magnitude probably won't change either, so it'll just be a drastic jump up and change. It's y double prime plus, yeah. Yeah, but the position itself looks like it would just change. So maybe it would just be a jump in that position. It would be, but it probably wouldn't be defined anyways, because there's a, there's this jump that happens, and so it becomes technically it becomes discontinuous at that point, and it just goes up. Because Laplace transform is good for piecewise discontinuous or piecewise continuous functions. I mean, in terms of the mass in the spring, your spring would just jump up to the next level, and there's an abrupt change, and so the derivatives might not be defined at those points. All right, let's try to do this problem and see what we get. And so I think we're already ready to jump to the Laplace world. So let's take it. Let's take it there. So they have s squared capital Y minus s times y of 0 minus y prime of 0 plus y, which is just y, is equal to, now we have a couple of delta functions. So this is going to be e to the negative 2 pi s plus e to the negative 4 pi s. And so we have these exponential functions in the Laplace world. When we bring it back, we'll see that shift happen in the real world. And so that part of the idea seems to be making some sense, I think. Let's put in the values that we have. The first derivative is equal to 0. The original function is equal to 1. So we have an extra 1 here. So let's factor out the y, the capital Y, s squared plus 1 with a y. And then let's bring this negative s over to the other side. So that's minus s plus e to the negative 2 pi s plus e to the negative 4 pi s. And then all this will get divided by s squared plus 1. So minus s over s squared plus 1. That looks like the cosine, right? And then we have e to the minus 2 pi s times 1 over s squared plus 1. That looks like a sine with a shift. And then we have another sine with a shift. All right, so as we get ready to go back, we remember some of our Laplace transforms. Um, all right, so we have Laplace transform of your cosine kt is equal to s over s plus s squared plus k squared, and then Laplace transform of sine kt is equal to k over s squared plus k squared. And then we have that shift. So the shift is the inverse Laplace of e to the minus s as capital F of s is equal to f of t minus a times u t minus a. So these are the things that we need. We should be able to go back to the real world now. All right, we have a negative, so this is going to start off with a negative cosine of t, and then now we have some shifts, and here we start to add things. We add s over s squared plus 1. Oh, this is negative. All right, so let's make that positive. All right, so we have the cosine t, and this is the shift with a sine. So this is going to be sine t minus 2 pi times the unit step function t minus 2 pi plus sine t minus 4 pi unit function t minus 4 pi. So if t minus 2 pi and t minus 4 pi are just sine functions, then it looks like they're just sine functions. So if we cosine t plus sine t times u of t minus 2 pi plus u of t minus 4 pi. All right. I think if I do graphing calculator, I have to define the unit step function, whereas Mathematica has it built in. Michael? One half plus what? For what? Oh, step function? I suppose we can. Yeah. So let's just do this cosine of t. What? Cosine delta what? Cos of t. What's going on here? What's happening? Plus sine. Huh. These weird things keep popping up. Unit step. What goes in a unit step? Yeah, so unit step t minus 2 pi plus unit step t minus 4 pi. Got my parentheses right. And so we want to graph this from 0 to, what's 4 pi-ish? 12. Let's go to 20. So 2 pi, 4 pi. Ticks. So there's some weird things that happen in the graph. The amplitudes seem to have grown a little bit. Yeah, you're hitting it right. It should grow, but I don't know. Okay. This is an interesting graph. Let's get that picture again. Let's get this picture in our notes. So the interesting aspects to probably look at in this graph is 2 pi and 4 pi, of course. That's when the shifts happens. And at the regular starting point from 0 to 2 pi, you just have the regular cosine function, right? And then from 2 pi to 4 pi, you have the cosine function, and then you add on the sine function. And then after that, you have the cosine of t plus sine of t plus another sine of t. I guess I should have said 2 sine t. So if that's the case, then they look like they have the same amplitude. They look like there's a little bit of a bump up here at 2 pi, and then the less subtle, but still a bump at 4 pi. And then you can find the amplitudes by just combining the sine and cosine functions together. Right, the amplitude is like the square root of the amplitude squared, something like that. So there's a formula to figure out the amplitudes. Yeah, but that's that. Any questions? Does it make sense physically? Or let's Josh answer your question first. I think when you're doing homework, if you have time, you should, in a test situation, I don't know if I would ask you to draw something like this in a test situation where you don't have access to a computer, because these, I mean, you can probably program the step function in your calculators, which is fine, but I think I probably won't ask you to draw the graph. I might if if I happen to have generated a bunch of graphs, and you could probably select one or something, um, like a multiple choice type thing. So yeah, but I wouldn't ask you to draw a graph just based on the calculator. Um, is this making a little bit more sense now than when we first started? Yeah. Oh, because I started down here, but I think you remember that the positive is is when you say you pull it down, that's a positive value, and so it started off with a positive. It's kind of like what we had here. Well, it's not as nice, but except the graph is upside down because we're looking at positive going down and negative going up. Anything else? All right, let's see if we can do another problem. What? How's your homework going? I don't know. You want to do a homework problem? The best way to study for this final. So the final is going to focus on the last two chapters that we had. So series and Laplace, well, Laplace transforms. Yes. So I would definitely want to know integrating factors and Bernoulli's and all those all those techniques that we've learned already. And I would also probably, in terms of dealing with series and in terms of dealing with series, wait, the answers are here. I would practice going through doing several series problems. Um, but I think the way I'm going to set up the problem for series is that I'm going to expect you to go from the beginning to the middle of a series problem, and then I'll change the problem going from the middle of the series problem to the end of the series problem. You know how series, we have to translate it and then do this index shifting, and then we find a pattern. So that's about, you find the C sub whatever. So that's about halfway through. And then once you find the C sub whatever, and then you find the pattern, then you write down your answers. That's like the other half. Yeah, so if you can't find the pattern, then I'll probably just ask for, the first 5 or 6 non-zero terms. Yeah, but sometimes it's not so easy to express the pattern in like a nice closed form. So no, I can't. I can't go over the quiz. If you want to see me in office hours or set an appointment, we can walk through the quiz. Yeah. Yes, probably not. Ordinary. Yeah. 6-1 and 6-2. Yeah. Wait, are we done? Are we done? So I probably need to give you another quiz, take-home quiz on this, on like the rest of the chapter 7. So no, the quiz. So you guys will have a quiz on Thursday, and it'll cover stuff from 7.4 and 7.5. It'll be in class. Well, because I'm realizing when I graded the in-class quiz, I'm realizing that, you know, some some people still need practice on this first step right here, changing your second derivative into the Laplace version of that. And so I want to make sure that everybody knows how to change a second derivative into the put that into the Laplace world. And if you can't do that, then so I want you to practice and know how to do that. And I mean, the formulas are all up on the board, right? You have to know how to use the formulas. So I want to give you another quiz on that. Alan? Uh, I'm not sure what's in store for next week. So next week we might do another worksheet, and we'll definitely review on Thursday next week. But on Tuesday, I'm not sure yet what we're gonna do. Yeah. 4 and 5. So the stuff that we did today, the delta function, we need to. I want you to know that, and so we'll write like last time. We'll write the formulas, a short part of the table on the board, and we'll write those theorems with the translation theorems and stuff as needed. Well, partial fractions was from Calc 2, so you should know how to do that. Theoretically. Only. Yeah, we're not going to do those. I might talk about chapter 8 a little bit on Thursday, but I'm not going to assign. I'm going to take that back. Tuesday? What? Yeah, so Tuesday, 11. We started 11. Tuesday, 11. 11 to 2. 11:10 to 1:40. I just rounded off to 11 to 2. Okay. Anything else? All right. Well, we can be done. Let's be done.